Methods and procedures for calculating pipe resistance will be described based on calculation examples. Samples will be used for explanation. So download the relevant data from the specified website and keep it close at hand. Some key points when selecting pumps will be also described. Introduction. Calculation of pipeline resistance is carried out to determine the level of resistance in the planned pipeline system and the required performance for the pump. Resistances are subdivided as follows. 1. Frictional resistance of straight pipes. 2. Local resistance. 3. Resistance of machinery. Frictional resistance of straight pipes, designated as item 1, is usually calculated by multiplying the specific pressure loss by the pipe length. This specific pressure loss is generally determined based on the friction loss diagram of each type of pipe. Local resistance, designated as item 2, is generated at deformed portions where pipes are bent, branched, joined, and transformed, or at valves. This resistance can be determined, for example, by multiplying the equivalent length by the specific pressure loss, or by multiplying the local resistance coefficient by the dynamic pressure. Resistance of machinery, designated as item 3, is generated in machinery including coils. Pressure loss is calculated using the following formulas. The Haven-Williams formula. The flow coefficient C depends on the type of pipe and the degree of dirt and rust, and becomes larger if the pipe wall becomes smoother. In general, the value 100 is used for old steel pipes, while the value 130 is used for new steel pipes. The Haven-Williams formula is applied to water pipelines at normal temperature. This formula can be applied to general chilled water in air conditioning pipelines. The higher the water temperature is, the lower the resistance is. If hot water is used, this system operates more safely. The Darcy-Weisbach formula. The Darcy-Weisbach formula is also often used. As can be seen in the formula, factors including effects of the temperature of the fluid and the flow rate are taken into account. Although there are differences in aging between open circuits and closed circuits, the formula is not basically used separately based on circuits. The AC data includes friction loss diagrams corresponding to individual pipes. Use those friction loss diagrams to determine the specific pressure loss of each pipe. Confirm required factors including the pipe type and the flow coefficient C before using such values. The AC data also includes information about various types of valves and equivalent lengths of elbows and T-joints. Confirm the resistance of machinery with technical materials including catalogs, specifications, and manufacturer's engineering data. If relevant resistance is not described on such materials, confirm it with the manufacturer and be sure to take it into account. Let's calculate pipe resistance using the system on the slide as a sample. Consider a series of pipes with the same pipe diameter through which water flows at the same flow rate through one particular section. Use that section for calculation. Assume that sections are divided by points A through V. The resistance of the section between A and B can be calculated as shown on the slide. The true length of the pipeline is the total length of the light blue lines shown in the isometric drawing. Use technical materials to determine individual equivalent lengths of local resistance elements while paying attention to the sizes and types of valves. The equivalent length of the butterfly valve is adopted for that of the gate valve. Enter the words equivalent to the length of the gate valve. The equivalent length of the vibration-proof fittings is also adopted for that of gate valve. The lift-type valve is used for a check valve to be set on the pump. The equivalent length of the globe valve is adopted for that of the check valve. The equivalent length of the Y strainer is adopted from other documents. The equivalent length of the elbow is also determined by paying attention to the sizes and types of them. Count individual numbers of pipeline elements based on the isometric drawing. Multiply each number by the corresponding equivalent length. Add up individual multiplied values to calculate the total equivalent length of local resistance elements. Add up all true pipe lengths and equivalent lengths of local resistance elements to determine the converted pipeline length. Determine the specific pressure loss, unit resistance, based on the size and the flow rate of the pipeline, and multiply the loss by the converted pipeline length to calculate the section resistance. The resistance generated in the section between points B and D can be calculated as shown on the slide. Equivalent lengths of local resistance elements including valves and elbows have been described before, so equivalent lengths of T-joints will be explained here. A T-joint divides a flow into two. The flow which passes through the straight side of the T-joint is called the straight flow, while the flow which runs sideways is called the branched flow. Before calculation, confirm which type of flow is used. Refer to the straight flow category, because the equivalent length of the straight side of the T-joint is calculated. The pipe size at the first branch is not changed, so refer to the not narrowed column in the straight flow category. The equivalent length is 1.3 meters. The size of one side of the T-joint is different from that of the other side of it across the branch point. Confirm diameters to determine the equivalent length. Here, the size of the T-joint changes from 65A to 50A at the branch point. The reduction ratio is 1/4, and the equivalent length is 1.7 meters. When you determine the equivalent length, refer to the upstream size of the T-joint in front of the branch point. The same equivalent length is basically used even if the T-joint is a branch type or a combined type and the size of the T-joint is enlarged or narrowed. The equivalent length of the straight side of the T-joint is 2.1 meters, because the size of the pipe is 80A and the reduction ratio is 1/4. Let's refer to the data for equivalent lengths of T-joints with other cross-sectional changes in shape. On the branched side, the pipe size is 80A. There is no difference in size. The equivalent length of the straight side is 1.5 meters. The reduction ratio is 3/4. The equivalent length of the branched side is 0.6 meters. As a result, the total equivalent length of the T-joint is 2.1 meters. The total equivalent length of the combined type T-joint on the slide is 2.1 meters. Because the enlargement ratio is 3/4, the equivalent length before the combined point is 0.6 meters. The size of the 80A pipes does not change, and the equivalent length of the straight side is 1.5 meters. Even if other T-joints with other sizes are reviewed, there is not so significant difference in equivalent lengths. Note, however, that the total equivalent length becomes longer if the size of the enlarged side is twice as that of the upstream size. A similar calculation can be used for equivalent lengths of T-joints following the first one. Explanation for them is left out. The resistance of this section between points S and U can be calculated as shown in the table. Determine the equivalent length in accordance with the method as shown before. Assume that the branched pipe is combined with the main line in the direction of the downstream side. Let's consider the branched side of the T-joint. Use the size of the pipe after the combined point when you determine the equivalent length of the combined type of T-joint. Here, the size of the pipe after the combined point S is 32A. Similarly, the size of the pipe after the combined point T is 65A. The equivalent length of the section between points S and T is 2.1 meters. The equivalent length of the section between points T and U is 3.7 meters. Resistance of each local resistance element is calculated as described above. Now, let's determine the total resistance of a pipeline by adding up individual resistance values. Take 10 to 20% of the allowance coefficient into account. Here, the allowance coefficient is 10%. The determined resistance is used in specifications of a pump. The unit Pascal is used to calculate the pipeline resistance. In addition, the pump head is required to know the pump performance. The pump head is determined by dividing the pipeline resistance multiplied by the allowance coefficient by 9.81. Select a pump by using the performance curve shown in material including catalogs published by manufacturers. In this calculation example, a closed circuit is considered. Calculation of resistance for open circuit scenes such as an open-type cooling towers require the pump head, actual pump head. Biased flow causes trouble including increased resistance and performance deterioration and damage to equipment. It is important to run the fluid as smoothly as possible. Reflect minimum requirements, including intervals between the pump and other resistance elements such as valves and elbows, during construction. If you find any improper spots on drawings or in construction sites, take appropriate actions. Finally, some key points to select a pump will be described. 1. Does the pump have any problem with the permissible backing pressure? If pre-charge pressure is applied to the suction side, It changes the withstanding pressure of the pump. Attention, therefore, must be paid to the specifications of the pump. Confirm the permissible backing pressure of the pump specifications. Two, confirm the conditions of the fluid to be used. Fluids to be used are specified based on individual pumps. Materials, sealing conditions, and mode output depend on factors including temperature, density, viscosity, and corrosiveness. Be sure to use the pump following the specifications complying with the fluid to be used. 3. Is surging of no concern? If the horizontal line of the head pump intersects with two or more points on the performance curve, the pump performance changes at operating points between such points on the curve. In this situation, the pump operation is unstable. Vibration and noise are generated. The pump may fail. Select the pump so that only one operating point can exist on the performance curve. In particular, select the operating point on the downward sloping part of the performance curve. Four, is there no possibility that cavitation will occur? When the static pressure of some of the fluid becomes equal to or lower than the vapor pressure corresponding to the fluid temperature at that time, the fluid is vaporized locally to generate air bubbles. This phenomenon is called cavitation. For centrifugal pumps, cavitation is likely to occur at the impeller inlet. If cavitation becomes more severe, noise and vibration are generated, and pump performance and efficiency drop. As a result, water cannot be sent. Additionally, if a pump is operated while under cavitation, severe corrosion occurs at the cavitation-generated portion and causes the pump to break down. To prevent cavitation, the effective suction head must always be larger than the required net positive suction head. This is very important. You can read the value of the required net positive suction head from the NPSH curve shown in the performance curve chart. The net positive suction head is determined by calculations based on operating conditions. The greater the resistance of the suction tube, and the hotter the water, the smaller the net positive suction head becomes. Cavitation is therefore likely to occur when the resistance of the suction tube has increased or when the temperature of the water is high. Cavitation is likely to occur around the cooling tower. Cavitation is likely to occur if the pipeline resistance on the suction side has increased. It may be caused by the clogging of the strainer, which increases the resistance. It also easily occurs if a control valve is installed on the suction side. You must sometimes confirm the net positive head and change the setting height. This is the end of the explanation of examples of pipeline resistance calculation and pumps.